All right, yeah. My name is Elijah Pelofske. I'm going to be talking about short-depth QA-OA circuits and quantum annealing on higher-order Ising models. This was work done with my collaborators, Andreas Berchi and Stefan Eidenbenz. All three of us are at Los Alamos National Laboratory in the Information Sciences Division. Yeah, so the motivation for this work was really specifically to perform a rigorous comparison between these two quantum algorithms, those being QA-OA and quantum annealing. And in particular, our goal was to do this analysis using current quantum computing hardware. And more specifically than that, we wanted to solve the exact same optimization problem, as close as we could make it to be native to the hardware. So this talk is specifically based on two different papers. You can see them on the slides here. One of these shares the title with this talk. These papers describe all of the technical details for these studies, which I will not be able to go into most of the technical details, but I will try to give you an idea of how we did this comparison. So I think that this is definitively the largest direct comparison between these two quantum algorithms performed to date. These used 127 qubit higher order Ising models. And this was motivated because both of these algorithms are the primary quantum algorithms for solving combinatorial optimization problems. Moreover, they are both very, very similar. They are actually both based on the same idea of adiabatic quantum computation, based on the adiabatic theorem in physics. So QA-OA, which can natively address higher order terms, we ran on the IBM quantum processor IBM Washington. This is a gate model system. And quantum annealing was run on two different D-Wave quantum annealers. The exact chip IDs were Advantage System 4.1 and Advantage System 6.1. Both of those devices have the Pegasus graph connectivity. So the optimization problems that we sampled are hardware compatible to both the heavy hex graph. Heavy hex is the name of the hardware graph of IBM Washington, and the Pegasus graphs, which are the names of the hardware graphs for the D-Wave processors. The Ising models, so the optimization problems that we looked at, contain higher order terms, specifically geometrically local cubic terms. This essentially makes the optimization problems harder. And D-Wave quantum annealers, natively what you program on them are linear and quadratic terms, so not natively cubic terms. Therefore, you have to perform what's called order reduction. Now, this order reduction we manually created to be extremely hardware compatible, and by extremely I mean no minor embedding on the Pegasus graph. So we also solved these Ising models exactly using Cplex to compute what the ground state success probability was for both quantum algorithms. We also solved them using simulated annealing. QA-OA was run with a transverse field mixer. What this means is that on D-Wave hardware, the driving Hamiltonian is your transverse field Hamiltonian. And kind of the analog in the QA-OA space, QA-OA being kind of a discretization of quantum annealing, is using that same Hamiltonian as your driver, meaning that these two algorithms are, again, very, very comparable. We ran QA-OA with 1 and 2 rounds. Here, rounds and that variable p denotes time steps. So this is how long we are running this algorithm. What you should expect is that if p is larger, or the number of rounds is larger, that means that we will get better solution quality, at least in a noiseless setting. And we also evaluated this kind of open loop control error suppression technique called dynamical decoupling on the QA-OA circuits. This is a gate model system error suppression technique. Yeah, so QA-OA, it's an acronym. It stands for the Quantum Approximate Optimization Algorithm, and this was generalized to the quantum alternating operator ansatz under the same acronym. The idea is that given some combinatorial optimization problem, in this case we're looking at variable states, which are spins, the objective is to find the minimum possible assignment. These are unconstrained optimization problems, but of course you could do the same for maximization problems. Generally, QA-OA follows this general framework of some initial state, then you have a phase separating Hamiltonian. This encodes what your cost function is, and next you have your mixing Hamiltonian, which again in our case is the transverse field mixer. And then we have some integer p. This describes how many runs we run the algorithm, how long we run it. And then we have two different real vectors, beta and gamma. These parameterize the phase-separating Hamiltonian and the mixing Hamiltonian. So the algorithm consists of preparing this initial state and then applying p rounds of alternating simulation of the phase-separating Hamiltonian and the mixing Hamiltonian. So the main important aspect about QAOA is that these vectors of beta and gamma angles, we need to tune. We need to select them such that we are able to obtain good solutions. So this is why QAOA is called a variational algorithm. You essentially need to perform classical machine learning or optimization loop on top of actually running these circuits to find good angles. And usually you don't know what these parameters, what good parameters are a priori, like before you've seen the problem. All right, so this equation describes our quantum annealing system. So our first term there, that's our transverse field Hamiltonian. That's what's kind of driving our system. And then our second term there is describing what our classical optimization problem is, right? What our Ising model is. There you can see our linear terms and our quadratic terms. Transverse field driving Hamiltonian. The parameter S in this equation is referred to as the anneal fraction. This kind of specifies at what point in the anneal you say, like what proportion of your transverse field Hamiltonian in your classical Ising model is encoded on the chip at that point in time. We use two different D-wave quantum annealers. For parameter tuning, one of the things that you can do with quantum annealing is you can modify the anneal schedules, and you can modify them in specific ways that we know can be beneficial, specifically for optimization problems. Namely, you can pause at some point in the anneal, hopefully near your critical point, which you don't necessarily know what it is, but you can try to sweep over some parameters of kind of pausing and hopefully get better solution quality. So that's the parameter tuning we did for quantum annealing. Here's the summary table of what the three device names are, what their topologies are, how many available qubits are on these devices, how many couplers / CNOT gates there are, and what the computation type is. So the distinction here being D-Wave being quantum annealing hardware and IBM Washington being a universal gate model device. Okay, so this is the hardware graph of IBM Washington. So this is kind of the network that describes natively what the hardware does. So each node here is a single qubit, and then kind of blue connections between the nodes. Those are operations you can do on the hardware that are 2 qubit gate operations. Those are your entangling operations. Now, the reason this is important is because the D-Wave hardware graphs are significantly larger than, sorry, is that me? No? Gotcha. All right. So the important thing here is that the D-Wave hardware graphs, as you noticed on the previous slide, there's like over 5,000 qubits on that device, whereas IBM Washington, which was the first IBM processor release that had 127 qubits, has only 127 qubits. And in order to do this direct comparison, even though the kind of sizes of the hardware graphs are so dramatically different, we wanted to define some problem, some optimization problem that would match both hardware graphs. And so we defined our problem instances, these are fairly contrived, to be exactly defined on the IBM Washington hardware graph. And that's what this slide is showing. This is an example of the optimization problem that we used. So here, red and green just denote the sign of the coefficient in the polynomial, so like in the cost function. And then the kind of ovals that are red and green just denote the geometrically local 3 cubic terms. So these are kind of like hyperedges, okay? And then each node just has a linear term, that is, it has a sign either +1 or -1, and then you have connections between the qubits, those are your quadratic terms, and they're also just +1, -1. So here we're kind of coin flipping to randomly generate instances each time in terms of the coefficients. The connectivity graph, though, is exactly the same. The point here is that it's essentially kind of a random spin glass, except that it is incredibly kind of contrived to be defined on this very specific hardware graph. And the point is that partially because this hardware graph is quite sparse, we can do some things like 3-edge coloring, and we can also have a nice bipartition. And so using this, we can define a very short depth QA-OA circuit. So here, what I mean by circuit is the set of quantum instructions that define the QA-OA algorithm. On the left-hand side, you can see kind of what this problem graph looks like, and then on the right-hand side, we're showing what the actual kind of digital circuit is. This is for a single round of QA-OA. I should point out that this circuit kind of handles the geometrically local higher order terms directly by doing only a single layer of single qubit gates. So the total CNOT depth here is 6 per P, which for context is extremely short depth. What this means is we can run this entire QA-OA circuit on the entire hardware graph in parallel, meaning it's a very shallow circuit, but we're able to do this on all 127 qubits, which is the largest QA-OA circuit experiment performed at the time. We've actually since then done up to 414 qubits. So this is what this circuit looks like. It's way too small for you to see any detail. The point here is that it's very shallow, right? So here each line is one of the 127 qubits, and we're doing only a few instructions on each qubit. Now, for D-Wave, as I mentioned before, we need to do this order reduction process. Now, we did not want to use minor embeddings because they can introduce some additional complications. It's generally better to represent the problem kind of closer to the hardware graph as much as you can. And so on the left-hand side, what we're showing are these little order reduction kind of gadgets, if you like. So here for each higher order term, we found a way to create an order reduction that matches the Pegasus graph exactly. And because we have different coefficients, we have to kind of swap between them. And then we have to kind of swap between them alternatingly as we embed these onto the Pegasus graph. So on the right-hand side, you can kind of see roughly 6 kind of roughly rectangular rotated blobs of color. Those are the embeddings on the Pegasus graph. Now, because the hardware graph is so much larger than 127 qubits, we could actually tile 6 of these problems onto the hardware graph. And by tile, I mean we can run these in parallel. We can execute parallel quantum annealing. And so in particular, what that means is whenever we get our samples back, we have essentially sampled 6 of these instances in just a single anneal cycle. Right? And then if we do this a bunch more times, we get more samples for free, essentially. This also helps us kind of mitigate some noise, right? If there's some parts of the hardware graph that have slightly more noise than others, for example. The point here I want to emphasize is that this kind of order reduction and native embedding onto the hardware graph was pretty non-trivial to do. It took quite a bit of effort to figure out exactly how to do this. But the effort invested here was to encode these problems on the hardware graph to get as good of performance as we can on D-Wave, similar to what we did in the case of QA-OA on the gate model devices. So both of these hardware implementations are highly, highly optimized, highly, highly customized. Yeah, so for QA-OA, one of the challenges with any quantum system really is you have this pretty horrible scaling if you try to simulate what happens to the system classically, right? This is sort of the main thing about quantum computing that's interesting. Now, in the case of QA-OA, for these specific circuits, they're actually, because they're kind of short depth, entanglement kind of grows very slowly. And so there is actually a way that you can classically simulate what's happening in the circuit, kind of roughly speaking. And this is called light cone kind of simplification. What I'm showing on the slide here is if you go out to 2 rounds of QA-OA, this is kind of the largest light cone of entanglement that you have to simulate classically in order to kind of compute the observable of the overall QA-OA circuit. You have to do this for like a bunch of different subgraphs on the hardware, essentially for every term in your polynomial. But my point here is that for 127 qubits, we can classically get an idea of what will happen when we run QA-OA circuits in a noiseless setting, importantly. So if we had no error rates at all on the hardware. For context, maybe 32 qubit simulations are approaching pretty hard for HPC. The upper limit is something like 50 qubits for kind of the largest supercomputers on Earth. Yeah, and so the idea here is that we can compute what will happen in a noiseless setting, given the parameters that we learn, and I'll show you how we do that in a second. And the point is that we want to compare this against the IBM Washington hardware, because the IBM Washington hardware is all quantum hardware does. Right now, there's some error rate on the hardware, right, being in the NISQ era. Yeah, and so this allows us to figure out exactly what the ideal QAOA performance is for these circuits, up to 2 rounds, which is important to note. If you go to more and more steps of QAOA, you get more and more entanglement in the circuit, and then it becomes harder and harder to simulate. So the experimental setup is we generated 10 of these random Ising models that have these geometrically local cubic terms. We also generated 10 Ising models that do not have any of these cubic terms. And we just randomly chose these coefficients. And then we sample all of these problems using simulated annealing, quantum annealing, QAOA, and we solve them exactly using CPLEX. This allows us to evaluate when and where the optimal solutions are found. And every one of these methods requires some order reduction to be performed, except QAOA. QAOA can do it kind of natively in the algorithm. The Ising models were embedded independently on the Pegasus hardware graph, unless there were any like missing hardware pieces that we ran into, in which case that wasn't possible for some of them. And this allows us to, again, execute many of these problems in parallel. The QAOA angles have some specific symmetries, so these parameters, the reason they're called angles is kind of because they parameterize these unitary simulations, and they are usually in multiples of like pi halves or so. But there are some symmetries that we can take advantage of to kind of reduce the search space. The way that we did angle finding for QAOA was we executed a massive on-hardware grid search for both p equals 1 and p equals 2. And the reason that I mention this is because that is extremely computationally intensive. It's also the most naive way to find angles, but we have never run into these problems before because we devised them. So we had no idea what parameters would work. And so, yeah, we went for just massive grid searches to find as good of angles as we possibly could. Yeah, and then on the D-Wave devices, we vary both the annealing times and the anneal schedules. So we use just default linear anneal schedules with many varying anneal times. Then we also try forward anneal schedules with pauses inserted, a variety of different pauses. For the QAOA circuits, yeah, we also test out this digital dynamical decoupling here. These are just pairs of poly X single qubit gates that can, in some cases, mitigate some noise. Each QAOA circuit is executed 10,000 times. Each QA quantum annealing Ising model and parameter setting is sampled 500 times. So the way to read that is because of the parallel embeddings, we get on the order of, I don't know, like 2,000 or 3,000 samples per parameter setting on the D-Wave devices. Here's the range of anneal schedules with pauses that we tried. Again, here we don't know much about these problems and where exactly the critical point may be. But we know that pausing in general is beneficial for optimization problems. So this is one of the schedule tuning sweeps that we run. So here each blue line is a different anneal schedule. I've just kind of combined these on top of each other. Okay, so here's the first result plot. Here what we're looking at are histogram distributions for all of the different solvers that I just mentioned. So I apologize for it being a little bit crowded. So here, the main thing to keep in mind is that we're looking for ground state energy. So lower energy is better. So here on the left-hand side, you can see it's about -200. That's the ground state, right? It's the minimum energy that you can possibly sample for this particular problem. The two green distributions, so dark green and lime, are the two sample distributions from the D-Wave hardware. Kind of light orange, salmon-ish color that's in the background, that's simulated annealing. So those three distributions are on the far left-hand side. Those are close to the ground state, and in fact, many times sample the ground state. So those are the best performing distributions. Okay, and then on the right-hand side, you have all of the other distributions. So centered at 0, kind of the cyan colored distribution, that is random sampling. The reason we put that in there is just kind of for context to see, what these distributions look like. Here, we're just randomly flipping a coin, 50-50 probability, to get some variable assignment vector and see what that energy is. And it is centered exactly at 0. So that's kind of like the worst case that you can do. Now, the QA-OA distributions, these are 4 distributions. They're on top of each other, and they're kind of in the middle between these 2 histogram distributions. That's the one that looks mostly orange in this plot. So these are the 4 QA-OA distributions for 1 round, 2 rounds, with and without dynamical decoupling. The main point here is that all 4 of those distributions performed pretty much the same. They were better than random sampling, but they were worse than quantum annealing. Now, the dashed kind of thick vertical lines that are yellow and greenish, those are showing what the exact QA-OA simulation mean energy would be in a noiseless setting. And the point is that P equals 1, as expected, is better than P equals 2 is better than P equals 1. As I mentioned before, kind of the idea of QA-OA is more steps you do, similar to quantum annealing, the better solution quality you will get. And we verified that in the noiseless setting. But on the hardware on IBM Washington, that was not the case because of the errors encountered during the computation, right? Because of the error rate on the device. The other thing is that what this means is that even in a noiseless setting, P equals 1 and P equals 2 for these problem instances, and for these angles that we found via grid search, you would still not perform as well as D-Wave hardware. That's what those lines mean. Okay, now here is a second plot. This is a different random problem instance, same setup though of what data I am showing. And the point is here is that the finding is exactly the same for this problem instance. The particulars of what the exact distributions are change, but same general trend. And we did this for 10 different problem instances, and all of those distributions look pretty much the same. These are just the first 2 as representative examples. Okay, now this plot is unfortunately even a bit harder to read. This one is an Ising model without cubic terms, so we've just taken out the cubic terms to see what the performance would look like. The findings here are pretty much exactly the same as the previous plots. The reason the axis scales are kind of confusing here is just because the ground state sampling, meaning like how often you sample the global optimal solution, is very high, which makes the y-axis kind of thrown out of scale. But again, here we see quantum annealing, simulated annealing perform very similarly, random sampling centered at 0, and QA-OA performs worse than random sampling and better than quantum annealing. And here's a 4th example, again, same trend. Okay, now in terms of parameter tuning, I'm going to show a few plots here. So here what we're looking at is mean energy for the different anneal schedules with pauses that we tried. The kind of minute details of these heat maps don't matter very much. The main thing to take away is that dark blue means better mean energy, and kind of reddish means slightly worse energy. And so, when doing these previous comparison plots that I just showed, we were using the absolute best parameters that we found in these grid searches. So absolute best QA-OA parameters and absolute best annealing schedule parameters, all right? So these direct comparisons are like kind of apples to apples. If you put in the same amount of optimization effort for both algorithms, or at least as close as we could get to the same amount of optimization effort, then these are the distributions that you would see for these problem instances. Yeah, and the other thing that I just want to mention here is that generally, especially for like longer annealing times, so kind of each of these different plots is just showing, so X and Y axis are different pause durations and where the pauses occurred. and then each of the 4 different subplots is just showing a different annealing time. The point is here that generally speaking, no matter what parameter you chose, the results are pretty good. Again, dark blue being good solution quality. Now, this is what the QA-OA parameter tuning that I've been mentioning so much looks like. This is what it looks like visually. So here, again, same setup as in a heat map. Kind of red is worse energy, blue is better energy. The X and Y axes are, this is for 1 round QA-OA. These are the beta and gamma angles. So here, these are just real numbers. And the thing to note, of course, is that basically you have to find this kind of blue region. You have to choose some parameter space in that blue region for QA-OA to perform well. And interestingly, you can also see kind of the symmetry of where it will perform worse, where you're starting to maximize the cost function. The axes on these heat maps show what the mean energy is across the sampling distribution. And so for context, right from the previous plots, we were looking at about an energy of -200 in the case of quantum annealing and simulated annealing. And in these plots, we see that the mean energy in that blue region is about -40. The reason that I put 3 of these plots up here is because these are 3 entirely different problem instances. And the kind of interesting thing is that even though these are different problem instances, the heat map is the same. So this was an interesting thing that we didn't necessarily expect. This is referred to as parameter concentration. These plots are from the noiseless classical simulation for these QA-OA circuits. Again, 1 round, and we see the same thing here, but here the heat map is considerably less noisy. The previous plots were computed on IBM Washington. All right, so this is a summary table of the ground state sampling success rates. So we're listing what the absolute ground state energy is for each of the 10 problem instances. Then we're saying what the simulated annealing minimum energy was, same for quantum annealing, same for QA-OA. And we also report how many times that minimum energy was found. The relevant thing to see here is that the quantum annealing minimum energy I think it always finds the ground state with 1 exception. And then in the case of QA-OA, the minimum energy is always fairly far away from the ground state. So it's a pretty unstable measurement. And for the problems with no cubic terms, we see essentially the same trend. Here, just the kind of sampling success rate is a bit higher for quantum annealing, for finding the ground state. Yeah, so these hardware-compatible optimization problems, along with the order reduction embedding on D-Wave Pegasus graph, as well as the highly optimized QA-OA circuit, allows for a systematic and rigorous comparison between the state-of-the-art hardware for both QA-OA and quantum annealing. QA-OA run on IBM Washington did perform better than random sampling. Both D-Wave quantum annealers performed better than QA-OA run on IBM Washington. And quantum annealing and simulated annealing performed similarly. Simulated annealing had slightly better, marginally better mean energy for the problem instances with cubic terms, which, as I mentioned, are slightly harder. They make the problem instances slightly harder. And we also found this pronounced QA-OA parameter concentration across the ensemble of Ising models. This is a phenomenon that has been seen before, but it was interesting to see in this case as well. A noiseless QA-OA computation would allow for p equals 2 to perform better than p equals 1. However, on IBM Washington, p equals 1 and p equals 2 performed nearly identically, with p equal 2 being marginally better when used with dynamical decoupling. So fundamentally, what this means is that QA-OA would need to be run at higher p, so more of these rounds, more of this angle parameter tuning, in order to reach the sampling distribution that D-Wave quantum annealers can currently compute. Yep, quick acknowledgements of funding at Los Alamos, and that is all. Thank you.